Okay, well, good morning, everyone. This Modern Nuclear webinar is part of Green Infrastructure Week, sponsored by AECOM, a week of insight and commentary curated by over 25 partners to highlight the technologies and innovations that will be needed to deliver the biggest gains in our global transition to net zero. You can find out more and see all the events at greeninfrastructureweek.com. The government's ambitions for nuclear power, including tripling nuclear capacity by 2050 and streamlining regulatory practices, has put nuclear energy back on the map. The plan aims to bump over £2 billion into the country's nuclear industry by 2030 and to deploy up to 24 gigawatts of new nuclear power by 2050. In this webinar, speakers will give short presentations on the delivery of large nuclear power stations, the opportunities for small modular reactors, SMRs, and developments in fusion energy. This will be followed by a panel session discussing the various options for modern nuclear and future opportunities. So, just a reminder then, if you have questions, please put your questions in the Q&A box. Happy to use the chat if you like to introduce yourself to other delegates, but please put questions in the Q&A box and we'll get round to those as soon as we can. So today we're privileged to have speakers from EDF Energy, Rolls-Royce SMR, and the UK Atomic Energy Authority, UKAEA, to provide an outline on their respective technologies. So to start things off, I'm pleased to welcome Shekhar Sumit. Shekhar is Head of Energy Transition at Sizewell C, the company developing the proposed nuclear project at Suffolk, UK. At Sizewell C, Shekhar looks after various work streams, such as the wider uses of nuclear energy, regulatory and government support, and investor engagement. Prior to joining Sizewell C, Shekhar was a senior associate in an international law firm's energy practice. So over to you, Shekhar.
Thanks a lot, Ray, and lovely to be here this morning. Let me just try and see if I can share my screen successfully. I hope you can see my screen. Thank you. Yeah. So, thanks, Ray. As Ray mentioned, I currently work in Sizewell C. I lead on our energy transition efforts. And one of the things that I'll be hoping to speak over the course of the next 10 or so minutes is both in terms of what we at Sizewell C are doing and the role that we see ourselves as potentially performing in our transition towards the green economy, but also not just the role that we directly can play in terms of driving that transition forward, but also what nuclear can indirectly do to achieve that objective. So just in terms of a quick snapshot, in terms of where we currently are with Sizewell C and what is it that we are doing. As Ray mentioned, Sizewell C is a proposed new nuclear power station in Suffolk. When Sizewell C is ready, it will be producing 3.2 gigawatts of electricity, which will be capable of meeting 7% of the United Kingdom's electricity needs. However, a key element of what we are looking to achieve with Sizewell C is its replicability with Hinkley Point C. So as people on this call might be aware, Hinkley Point C is a new nuclear power station currently being constructed in Somerset. So that Hinkley Point C power station, of course, is a genuine first of a kind project in the respect that we really did not have that many nuclear projects being developed over the last few decades. So Hinkley Point C was a first of a kind project in that respect. However, what Sizewell C will benefit from is all the work that has been done insofar as Hinkley Point C is concerned, because Sizewell C will be replicating all the Hinkley Point C arrangements. So we'll be benefiting from all the skills, experience, and knowledge that is being gathered at Hinkley Point C right now, which will mean that not only will we benefit from we reduce construction costs and all the knowledge that comes along with a replication-based approach, but also in terms of when we go and engage with the financing community, with investors, and even when we speak about financing costs, because of the second of a kind nature of Sizewell C, that has a lot of positive attributes insofar as that aspect and element is concerned as well. Not to mention the fact that insofar as various regulatory approvals and processes are required, because we're using the same UK EPR technology, there are benefits insofar as that aspect is concerned as well. So in a nutshell, where we currently are with Sizewell C is we do have that detailed buildable design, which comes from Hinkley Point C. We have been in lots of fairly intensive discussions with government over the more than the last year or so, all of which are progressing well. As people on this call might be aware, and as Ray mentioned, government of course published the energy security strategy earlier this month, which speaks to the role that nuclear can play in a future green low carbon ecosystem. The Nuclear Energy Financing Act also received royal assent a few weeks back. And of course, that act lays the foundation stone for the regulated asset-based model, which we will be using Innovate to drive the financial structure of Sizewell C forward. We submitted our development consent order after years of consultation, so we're hoping for a final planning decision on that soon. And we have also applied for a nuclear site license and other environmental consents. However, one of the aspects that I was hoping to speak to, in addition to the role that Sizewell C itself can intrinsically play in terms of driving the green ecosystem forward, is a wider role that Sizewell C can play insofar as driving forward other innovative technologies. So traditionally and typically, of course, nuclear power stations have produced low carbon electricity and provided it to the grid. However, nuclear power stations and nuclear projects in general, in summary, remain these massive sources of low carbon heat. And of course, that heat then in turn is converted into electricity, which is then provided to the grid. However, there is the potential for nuclear energy to not only provide low carbon electricity to the grid, but also seek to use the low carbon heat before it is converted into low carbon electricity, and in a way use that combination of heat and electricity to drive a number of use cases and applications forward. So if you look at the diagram on the left-hand side of your page, what you see as arrows essentially are different energy types that nuclear energy can help in driving forward. So you have, let's say, low carbon heat, low carbon electricity, which are marked in the arrows in orange and blue. What you see in circles are energy vectors that those energy types can help in driving forward. So for example, if I pick hydrogen as an example, you can produce hydrogen by steam-assisted electrolysis, which you can essentially drive forward by combining low carbon heat and electricity from a nuclear power station. And then what you see in the squarish shapes are the eventual use cases. So you can then use that low carbon hydrogen to drive forward various transportation use cases. What I have set out on the right-hand side of that particular slide are just a few examples of potential applications that we, as a nuclear project, can look to drive forward. So I'll come to hydrogen and direct air capture in the subsequent slides, but also there are other applications such as, say, district heating or cooling data centers. So there are a number of synergies that nuclear energy can have with a number of other innovative energy use cases, which then again can play a very significant role in driving us forward towards a low carbon energy ecosystem. I specifically mentioned hydrogen because, again, hydrogen is something, it's an energy vector, which of course is really important. It's something that the energy security strategy also referred to in a fairly significant amount of detail as well. And as Sizewell C, we look at hydrogen essentially in two regards. So one aspect is production-based, which ties into what I had mentioned in the previous slide, which is you can use a combination of low carbon electricity and low carbon heat to drive the hydrogen production process forward. And that production process will be more efficient than just using a plain electrolysis-based process alone. Now that, of course, is tied in with an operational, Sizewell C nuclear power station when it does become operational in a decade or so's time. But what that then can do is, because you're using that combination of low carbon heat and electricity, it will be more efficient. Because you're using baseload nuclear energy, that will result in reduced rates of electrolyzer degradation. And also what nuclear offers is an ability, for example, to work with offshore wind or renewable sources to drive that hydrogen production case forward. But that, of course, is linked with an operational, Sizewell C. In the shorter term, though, what we're also looking to do is using hydrogen buses and construction equipment to decarbonize Sizewell C's construction process itself. Now, just given the scale of Sizewell C's construction and given the number of buses that we'll have flying on site, it's a really, really significant consumption use case that we as Sizewell C are offering. And instead of, say, using diesel to drive forward the various buses or construction equipment, we are looking to use low carbon hydrogen to do so, which will serve to drive forward both the hydrogen economy, because as we will be a fairly significant consumption use case. But at the same time, what we're also looking to do is we're interacting with other stakeholders in the area who are also interested in using hydrogen for their use cases, such as the ports in the region or local councils, so that we can serve as a demand aggregator and a catalyst. Moving on, one of the other use cases that we are also very actively exploring is direct air capture. Direct air capture, as some people on the call might already be aware, is a means of essentially absorbing carbon dioxide from the atmosphere. So it is slightly similar to carbon capture processes. However, the way in which it differs is because the atmospheric concentration of carbon dioxide is quite low. It's around 400 parts per million. So the kind of chemical substances and sorbents that are used differ slightly from what is used for other typical carbon capture use processes. So we have these really, really interesting sorbent substances which are capable of absorbing carbon dioxide from the atmosphere. But the main input for direct air capture is actually heat, because once these sorbents capture carbon dioxide, it is then subjected to heat at certain parameters and conditions. And then after that, the carbon dioxide is leached away from the sorbent substance, which is then fit for reuse again. And that is again where a nuclear power project such as Sizewell C can make a very real difference. So in terms of extracting heat from the nuclear power station, and then in that that heat can be provided to the relevant sorbent substance, which can help drive this direct air capture process forward. So government actually recently launched a competition called the Greenhouse Gas Removals Competition, which we as Sizewell C participated along with a consortium of engineering and academic institutions. We were successful in the first phase of the competition, and we carried out a desktop feasibility analysis of how such a direct air capture project could work. And we have actually put forward an application for phase 2 of the competition as well, which entails the development of an actual physical prototype of how such a direct air capture unit could work. And just to give you an idea as to the scale of the difference that this technology could make, given the amount of heat that we're looking to extract from Sizewell C, if that were to be used for a direct air capture unit, that could be capable of capturing 1.5 billion tons of carbon dioxide per annum, which is almost enough to offset the entirety of UK's annual rail emissions at this point. And the final slide I just wanted to quickly speak to you about today was, again, just touching upon that point of synergy that I mentioned earlier. We are currently working with the ports of Felixstowe and Harwich, which were awarded free port status last year in terms of their low carbon plans as well. And then they see hydrogen as a key element of driving forward their low carbon aspirations. So in terms of, for example, the various onshore and offshore processes, using hydrogen or low carbon synthetic fuels instead of relying upon diesel or more polluting fuel factors. And that is again something where, as Sizewell C, we see nuclear can play a role directly by way of providing low carbon electricity and low carbon heat, but also indirectly in terms of driving forward these production use cases, for example, insofar as production of low carbon hydrogen is concerned. And over here, as Sizewell C, we can work with the port itself. We can work with offshore wind in terms of driving forward that production case. We can work with the local councils, for example, the infrastructure such as refueling stations and other aspects. That is something which should benefit the local community as well. And in a way, it can help in the creation of this ecosystem where everyone plays their role, their part in driving forward this low carbon vision forward. So, and then the final point I'd just quickly like to mention is, as I had mentioned towards the beginning of my presentation, a key element of what we as Sizewell C are trying to do is replication from Hinkley Point C. given all the efficiencies that it will provide. So what we are looking to explore is the elements I mentioned in terms of extracting low carbon heat in a way that does not affect that replication case. So which means that all the various approvals that we had previously gotten from the regulatory authorities, within the boundaries of that, what is it that we can do so that we can play a far more expanded role in terms of driving forward this low carbon vision forward. So yeah, this was a very quick canter through what we as Sizewell C are looking to do. I'll just stop sharing my screen now. And of course, very happy to field any questions during the Q&A session. Thank you.
Thank you very much, Shekhar. That's a really interesting presentation, and it shows the flexibility large nuclear plants have to have moving forward, as I say, in this modern nuclear sort of session. Well, one question I have, I don't think we've got any specific questions as yet on that, so very clear, concise presentation. Obviously, you say it's a replica from Hinkley Point C, but is there any scope in terms of for Hinkley Point C to produce, hydrogen, retrofit any direct air capture, etc., or is design totally fixed?
Oh no, I think that's a really, really good question, Ray. And in answer to that, I'd probably try and answer it in for two themes, if I may. So the first theme is from an engineering perspective. I think, yes, absolutely, Hinkley Point C ought to be able to play a role insofar as driving forward some of these innovative technologies are concerned. And to the extent that any engineering modification works are required, that is something, of course, that can be carried out. And in a way, that is what we're trying to do at Sizewell C as well, as in what is it that Sizewell C can do, retaining the replication safety case element. So that is potentially something that Hinkley Point C may be able to do as well. So that is from an engineering technical perspective. However, and it's perhaps a slightly important however, the economic case for Hinkley Point C is linked to the contract for difference model. And the revenues are, of course, linked to the amount of electricity that Hinkley Point C puts onto the grid. Now, to the extent that we are extracting low carbon heat from a nuclear power station, that then means that that low carbon heat will not be then used for the production of electricity. So there is a small element of opportunity cost associated with electricity that is not put onto the grid. Now, the economic model that we are discussing in the respect of Sizewell C right now is, of course, different from the Hinkley Point C model. And what we're trying to ensure is that economic disincentive does not exist to the extent that we are looking to use low carbon heat to drive forward these other innovative processes. So of course, it can be done with Hinkley Point C, but it may just require a bit of discussion to ensure that it can play a similar role in driving these technologies forward. Excellent,
thank you. Just revenue then, never mind. Okay, that's great. Thanks very much, Shekhar. So moving on to Rolls-Royce small modular reactors, I'd like to introduce Mike Crawford. Mike is the business development manager for Rolls-Royce SMR, developing new ways to apply a zero carbon solution to the energy markets of tomorrow, with a specific focus on transforming the industrial applications of nuclear power. Mike has over 10 years in the nuclear industry, time spent working across a variety of new product introduction programs, including the UK's Dreadnought submarine program and an innovative lunar surface fission microreactor. Interesting stuff. Okay, over to you, Mike.
Thanks, Ray. So yeah, I'm Mike Crawforth, Business Development Manager at Rolls-Royce SMR, and I've pulled together a quick presentation to talk you through some of the interesting kind of infrastructure aspects of what we're doing over at SMRs. So firstly, who we are. Rolls-Royce SMR is now it's a separate privately owned company. So it was formed at the back end of last year with a successful fundraising round, raising 490 million in a mixture of private equity and government grants. Rolls-Royce, as you might imagine, is the major shareholder here, hence we've brought along the name and the brand, which is great, but we also import a huge wealth of manufacturing experience and over 60 years in the nuclear industry, both in a civil and defence space. So that's a strong start, but in addition to that, we have Constellation, who were formerly Exelon, and they're the US's largest operator of nuclear fleets. So having a nuclear SQUET or nuclear qualified operator on board on the team really helps us as we move from design to deployment of this technology. In addition to that, we have BNF Resources and Qatar Investment Authority, both of which are investing heavily in the clean energy space in a variety of low carbon energy generation techniques and technologies. So all of that is going to be useful as we have to bring all of these technologies together to really decarbonize, society as a whole. So in addition to those shareholders, we have UK government support in the form of £210 million from the Department for Business, Energy, Industrial Strategy and UKRI itself. So it's really great as we try and deploy this solution globally that we have not just the support of one government and that vote of confidence, but actually two on the board here. So yeah, really good. And none of that mentions the consortia partners that we bring with us from phase one as part of the UK SMR consortium, a number of infrastructure partners on there indeed. So what differentiates Rolls-Royce SMR or SMRs in general from the nuclear technology that's come before? So this is modern nuclear, but also the other kind of technologies we've got on the panel here today. And somewhat flippantly, it's the word small and modular, because I've seen a lot of criticism in the press recently around the use of the terminology small modular reactors and what does it even mean, modular, what's that? And I'm not a linguist, but it feels fairly self-evident that these things are smaller and made up of individual modules. And there really isn't that much more to it than that. So the Rolls-Royce SMR is designed to be modularized across the whole power station. So not just the reactor island and those, the pressure vessels, the steam generators, the pumps, the valves, but also the whole power generation system. So, turbo generators, cooling, water, all of that is modularized. Even the civil construction elements are modularized. So completely new way of building nuclear. What we do with all those modules, we do factory assembly, and then we road transport them to the various sites. We construct at site in what we term a fourth factory, so a canopy with craneage and that sort of thing. And that really guarantees the build certainty and protects us from the weather, even in the UK, to give us that build certainty and schedule certainty. And essentially that's what this is all about. So the modularization is there to drive down cost. It's not there to be novel for novel's sake. It can improve the reliability through building in the factories and having that guaranteed environment. It improves the economies of scale, as we start to really bump up the number of deployment of nuclear in the UK. We're predicting, not necessarily in the UK, but we're predicting global deployment, in the tens, hundreds of SMRs. We can reduce build time through this approach and paralleling multiple operations and reducing the amount of time spent on site. And also critically, it creates long-term stable jobs in the factory locations, removing that boom and bust model. And critically for us, it ensures we have that resource certainty. We can employ long-term employees that we know we're going to have the skill sets when we need them, and it gives us that predictability. So that's one of the major differences for us. And this is what it looks like when it's all said and done. You may have seen certain images of the finished product with an architecturally significant canopy and green bunding around the site. That is all present, but here is the nitty-gritty infrastructure that I'm sure you all want to see as the audience today. What we have is 470 megawatts net electrical output from a plant that fits within 0.145 kilometers squared. And that's the takeaway point really of what the Rolls-Royce SMR is all about. All of the nuclear technologies here today, are going to showcase the energy density that nuclear can offer. And when you compare that to wind and solar and other renewables, it's just orders of magnitude higher. And that's what earns nuclear a place in the future of our energy systems, because it's going to be critical as we look to reduce our costs, our land, our resources, but critically give us stable supply. So I'm going to touch on a different advantage of nuclear to renewables. And we know a lot about intermittency. Renewables suffer from intermittency. We hear that a lot. And what that means is nuclear is great for baseload because it's always outputting energy. And that is absolutely true. Nuclear is great for baseload. But actually what constant assured energy gives you is it's great for economics. All of these power generation technologies aren't generating power for power's sake. There's useful activity going on at the other end of those wires. If that useful activity and that equipment doing the useful activity is only active for 20% of the time, then you've spent an awful lot of money to get 20% of use out of it compared to someone who's getting 100% use out of it. And if that useful activity is, say, making hydrogen that's going to be heating homes, powering industry, then we really need to make sure we're comparing apples and apples with making decisions on how we create that balanced and integrated energy system. So just very quickly here, I'll talk you through, if you compare wind and solar to nuclear power station, say 470 megawatts electrical, you can install that much capacity of wind and nuclear, but you're not going to get it all the time. So if you really want to match like for like with assured 470 24/7, you need to install over capacity by a significant margin, and the energy storage, whether that's via batteries or something novel like hydrogen, to match. And that really starts to ramp up in terms of cost, land use, resources. Now you can quickly see some numbers here. If anyone's screen grabbing, you can look at these in slow time. But essentially, this just shows what I've just talked about. And we often hear nuclear is too expensive, it's too slow. Well, you look at some of the numbers here in the left-hand side, and actually, well, nuclear does seem more expensive than wind. It seems a lot more expensive than solar. So there's the answer. Let's just build loads of solar. But unfortunately, the sun doesn't always shine. And I'm being generous with that example because that's got a capacity factor of 30 from a plant in India. Now, in the UK, you're lucky if you get anywhere near 20. Sometimes it's 11, really, depending on where you are. So, not only do they not last as long, you're not getting that capacity factor, and you need a hell of a lot more land area to achieve that same capacity. And as we just discussed, it's not just that capacity, because if you really want the same amount of energy, you need to install overcapacity and energy storage, which adds additional land use, cost, resources. And it all starts to add up, and the rose tinting, quickly falls off when you start to look at it a bit closer. And so I think we sometimes get an unfair comparison there against renewables. This is the timeline for Rolls-Royce SMR. We finished phase 1 at the end of last year. That was concluded with our fundraising and the establishment of Rolls-Royce SMR as a private entity. Phase 2 is what we're in now. That was signalled by entry into the UK's GDA process. So that's the regulatory design approval process. And that will make up the focus of phase 2 over the next few years. In parallel to that, we'll be securing our first orders imminently. So that's essentially what phase 2 is about. Then we'll move into phase 3, which is about preparing for delivery of the fleet, building up our capacity. There's a big challenge here. We're very firm now that our first of a kind will be operational by 2029. And that's been driven by the kind of stark reminder that we've had over the recent weeks and months of how precariously balanced the energy security is in Europe and indeed the world, and actually how reliant we still are on fossil fuels, whether from Russia or elsewhere. We're really not in a situation that is sustainable into the long run. So we're committed as a team to meeting this target, and it's something that it impassions us every day and is what gets us out of bed. But nonetheless, it is a challenge. So to step up to meet that, Rolls-Royce was already designed, with speed of deployment in mind. This is one of the along with cost and route speed to market, that was the core tenet of the design process. Get a product out there that can start contributing and delivering clean energy. So we made a number of design decisions from the outset with that in mind, which was using existing PWR technology. It's proven. Utilizing off-the-shelf components, again, proven, that is justified, that can be scaled rapidly. We're creating an organizational kind of construct from the get-go that is ready for global deployment, and it's ready. It's not just a technology provider. We're setting up that infrastructure to do the full deployment solution for our customers. And with that, we provide as a technology partner the full power plant, not just a reactor. So yeah, that's about it. I mean, on the bottom here is transparent pricing, and we pride ourselves on being a transparent organization inside and out, and that's because we feel we have nothing to hide. So, if anyone has questions, please feel free to contact me. This is an example, much as we've just seen, of what an integrated energy system could look like in the future. And, I'd like to caveat, I have nothing against renewables. We need more renewables and we need them yesterday. But renewables alone are not suitable for the scale and type of the challenge that we face as to decarbonize, every facet of our society. So these are the sorts of integrated systems we could expect. And, there's a lot of uncertainty as we go forward into how this is really going to play out. Rolls-Royce is pursuing a number of technologies as a group, and that's a great advantage that we have, being able to lean into that technology capabilities across the whole group. It's going to be really important for us. So actually, direct air capture is something we're developing in-house. Fuel cells again. So really trying to pull all this together, into a smart, workable energy architecture. And that's it from me. So I'll leave you with this slide, kind of summing up what we're about, and that essentially Rolls-Royce SMR is a new way of building nuclear to meet the needs of net zero, and to do that we've made sure that it is low cost, it's deliverable, it's scalable to the challenge, and most of all, it's investable. So that's it from me. Thank you.
Thank you very much, Mike. We do have some questions for you. So then, just looking at the time now, so perhaps we'll take a few, and then perhaps you could take a look at the Q&A and see if you can answer some there. But we'll start with, there's a question from David Dundas. Did the Rolls-Royce SMR require a safety containment building?
So yes, so there's, the regulations, so I'm used to speaking with nuclear and non-nuclear audiences, so I'll try and tailor the response, assuming this is a non-nuclear audience. The nuclear regulator mandates various requirements on safety features and systems to make sure that any deployment of nuclear technology, whether that's a power plant or otherwise, is safe, and that no harm will come to the public or environment. So as part of the Rolls-Royce design, there's kind of a hazard shield. So the nuclear bit in the center, the core with the pumps and the coolant, that is all contained in a sort of shell, protective shell that protects from anything that could go wrong inside, to make sure nothing escapes into the environment. The building itself, the kind of concrete, the steel, that then has its own requirements to make sure that planes can't fly into it and all that sort of stuff. So yes, there's various levels of safety and containment. There is a baseline part of the design, and it's mandated for deployment.
Thanks, Mike. One question here from James Louch. What considerations have been made for decommissioning of SMR plants? Timelines, specific activities, storage of fissile materials, etc.?
Yeah, good question. So the plant lifetime for an SMR is designed to be 60 years. We think we could probably go higher than that, but that will be a decision that we made once we've got operational experience, and you can see how things are progressing. But you could expect to get maybe 80 years out of an SMR. Now, you will generate kind of used fuel through that. All the fuel is designed to be stored on site for the life of the plant, until it's safe to then be moved to a long-term storage facility. So it's been in the news recently. In Finland, we actually are opening up one of the world's first kind of long-term nuclear waste storage facilities, which is great news, and it's something the UK is looking to emulate. So for the life of the plant and beyond, the design incorporates the storage of those used fuel. And decommissioning is factored in. So part of the operational costs, we pay a decommissioning levy. So you sort of, throughout the lifetime of the plant, you build up a set fee that at the end of plant life will pay to take it all away and return the land as was. So yeah, things have changed in regulation space, compared to when some of the first nuclear plants were installed many decades ago.
Okay, Thanks, Mike. Tell you what, we'll take one more because I think it can be answered quickly, but perhaps you could take a look, Mike, at the other questions and perhaps type some answers. But there's another one from David Dundas here. Why has Rolls-Royce decided to use PWR technology rather than low pressure molten salts or metal cooling technologies?
And cost, speed, well, cost, but speed as part of that was the answer, really. We wanted to make something that the levelized cost of electricity was as low as possible. So taking that existing technology that works and getting it out there was the quickest solution, or the best solution.
Excellent. And as I say, I think it's existing technology, isn't it? There's a lot of work going on in advanced nuclear technologies around molten salts and liquid metal cooled reactors, but as yet, nobody has one. So the focus on existing technologies. And of course, Rolls-Royce, you understand the PWR technologies very well as well. That's great. Thanks very much, Mike. Thanks for your questions. We'll get round to those as soon as we can, and perhaps, as I say, Mike can address some of those by typing an answer. Next, then, we would like to up on the screen. There you go. I'd like to introduce Heather from UKAEA. Heather Lewtas is the Head of Innovation at the UKAEA, managing the innovation pipeline process and helping to find and capture and develop innovation opportunities wherever they arise in the Fusion programme. Heather was previously the Strategic Operations Manager for STEP, which is the Spherical Tokamak for Energy Production, which is an ambitious programme to design and construct a prototype fusion energy plant, as well as the lead of multiple manufacturing programmes across UKAEA. Before joining UKAEA, she worked in the defence and aerospace sector, running technology programmes on materials and structures, and in the spacecraft instrument at Imperial College London, having received a PhD in physics from the University of Oxford. So over to you, Heather. Thank you very much.
Thank you very much. Rundown of my life. Right. Hopefully, we'll show you the nice.
Yeah, see that?
You can see it full screen.
Yeah. Oh. No, not full screen. You got notes at the moment.
Right. Hi everybody. Lovely to be able to speak to you today and tell you about particularly the delivery elements of fusion energy. So I'm speaking to you from the United Kingdom Atomic Energy Authority. So we're the UK National Fusion Lab, and we have this mission here, which I always start with, which is to lead the delivery. That's very key here, of sustainable fusion energy. And while doing that, make sure we maximise the scientific and economic benefit of everything that we are doing. I've got a few very quick slides on fusion. In case people were not quite up to speed with it. So the process that powers the sun does it by fusing hydrogen at the core. The way we do it is by fusing light hydrogen, so deuterium and tritium, and we heat this plasma up to 150 million degrees, so 10 times hotter than the center of the sun. So why do we do it? Why would we do that? So there are a lot of benefits of fusion energy. First of all, its low carbon nature. So it's low carbon, it doesn't produce carbon through the process. It's low land usage. That's been mentioned before in these presentations for nuclear. It's safe. The process inherently is very safe. It's very difficult to actually create this plasma. If anything disrupts it, if you overfuel it, overheat it, it just stops. It is very, very safe, controllable process. It's reliable. You've heard about baseload already. It doesn't depend on the seasonal variations that you might get with some other processes. Our fuel source is extremely sustainable. You get deuterium from seawater and lithium that we use for batteries, those sorts of things. So there's an abundant source of the fuel that's needed. And it's also extremely energy efficient. So it's the most power dense process that would be available to us on Earth. So that's why we want to do it. Now, a lot of people, I get the question, well, when will fusion be possible? And the answer really is fusion is possible now. It is happening here. It is happening across, the UK, around the world. It's happening in experimental reactors. So you've got a few here, and picked out the ones that are either currently in the UK or where you can see the artist's representation will be in the UK. So the Joint European Torus has been running here on the Culham site near Abingdon, near Didcot, since the early 90s. So a lot of experience in running this reactor. We've also got a spherical tokamak called MAST, and then there are private fusion companies. You've got First Light and Tokamak Energy here, also sort of within the Oxfordshire area, who are doing fusion now. And this doesn't even touch on all the reactors around the world, the big global fusion endeavour, ITER in the south of France. These are experiments, but what they're leading to is the delivery of fusion as an electricity producing source. This is where we are getting to, and why we believe that fusion now is the time where we can say that we're entering the delivery era. But what this really means is that we need to consider the economics of what it is that we're doing, consider the economics of this future fusion power station. The cost of the power station itself, which isn't the fuel, that's pretty cheap. The power output, so getting more power out, obviously, than you put in. And this is all going to be contingent on developments and progress that have been made so far to date, and we still need to make. So this is developments in plasma physics, technology, and engineering around that. And this goes as well for the availability. So the fraction of time that the plant is running, this is a big part of fusion now. How do you design it, design your materials, design your components, so that they are up and running for as much time as possible. Now, there's different projects that are looking at this delivery. The first one I want to talk about is STEP. So STEP is a UKAEA project, spherical tokamak for energy production, and it has a very ambitious aim. So a UK prototype fusion energy plant targeting 2040, but with that, the path to commercial viability. So making a prototype, which really is the blueprint for commercial reactors. So why do we think that we can do this? And why do we think that we could do this in the UK? This is a diagram that I particularly like because it shows how we've been building up to this belief that we're entering our ability to deliver fusion. Right the way from the 1920s, 1950s, where a lot of work has been going on within the UK on fusion energy, developing the plasma physics, developing the engineering. And this has been gradually bringing us up this mountain. And it's why I think in the UK, we're in a really great place to be able to deliver fusion energy because we have these skills, we have this experience. The jet tokamak, which we have here on site, is the only tokamak in the world which has been running deuterium and tritium. The experience that goes along with that and having operated this for decades is huge, and why we believe now's the time to really go for this prototype fusion power plant. Now, nothing says delivery and build quite like choosing a site. So this is the STEP siting timeline. As you can see, we're quite a way through this. So a call was put out in 2020 asking for communities to nominate themselves as a potential site for this STEP reactor. A lot of work has gone on creating a long list of 15 sites, a short list of 5 sites, and then working with these 5 sites and doing a detailed analysis of them all. We're now at a point where a recommendation has been made, and by the end of this year, the Secretary of State will make a decision about where STEP will be built, where this fantastic and particularly ambitious infrastructure project will be sited. So that is the project STEP. There is a huge and growing energy impetus behind fusion, and nowadays a lot of it being private fusion as well. There are lots of national labs around the world, but private fusion has been growing in the last couple of years. I mean, hugely. By the time you put numbers and statistics like this, they're out of date by the next day. There were 23, as of October 21, 23 private fusion companies. That will be more now. And they are raising huge amounts of funding. This is because people believe, first of all, it's really needed, and that it is possible. And the great thing about all these different ways of approaching this is that it's new ideas. It's approaching things from different perspectives, and across all these ideas, some things will work, some things won't. And the fact that people are approaching this in a different way really is great. And what we need to do when people are approaching things in different ways is we need to try and bring people together and make fusion happen as fast as possible. As Fusion Lab, having operated for decades, we've got a lot of experience, not just with the sort of core bit making the plasma, but everything that goes along with it, which other people don't have. Other people can come and learn from. So what's been set up is a fusion cluster, which involves not only us, some of the private fusion companies, but also some of the large engineering companies and industry and even academia who are getting into the fusion game, really going to be pushing for delivery of a fusion power plant. So this is the fusion cluster, which is being set up by people at Cullen. This is a very whistle-stop tour in 10 minutes of delivery of fusion. But I think this shows the breadth of different approaches, but that there is a collaborative element in here because of the need to make sure that we make this happen as fast as possible. When you're looking at the net zero targets for 2050, obviously, if I'm saying STEP will be there by 2040, we're not going to make a significant contribution to net zero by 2050. What we will do is, after that, be a big part of maintaining that and providing that baseload energy for all the benefits I mentioned before. Now, as head of innovation, what my job really is to do is to look at the technology transfer of this. Fusion is different, but there is huge overlap with all different sectors, with fission, with oil and gas, with just so many different things that we need to learn from. So there's a big push to bring in useful technologies from other industries. So making sure that we really communicate what our challenges are. If people know the things that we need to overcome, hopefully they will be able to approach us with solutions. So there are lots of challenges put out. There's a fusion industry program where we really do communicate what these challenges are, hoping that there are people who can come in and bring new ideas and help us really bring in that diversity of knowledge. And this is across robotics, superconductors, diagnostics, process engineering, really just a huge swathe of what we're going to need to do to fusion. Another thing that we need to do is really show the short-term benefits of fusion. Because when you're targeting 2040, that's ambitious as it is. But what we need to do is demonstrate the benefits of fusion as we're going along that route. So technology transfer from all these innovations, all this work that's going on into other industries. So people can see what fusion is bringing, even as we're going along that journey for the prototype, and then beyond to a commercial reactor. So we've got a big push on this at the moment. And then my final slide, and this is an answer to when will fusion be here? And I think it's when it's really needed. And so this is a quote from Stephen Hawkins. What world-changing idea would you like to see implemented by humanity? Which he said was easy. He'd like to see the development of fusion, which would give an unlimited supply of clean energy. So that is what we're going to try and do. That is me.
That's brilliant, Heather. Thank you very much. And a brilliant sponsor to endorse your technology. Well, that's not bad at all. That's great. We have a couple of questions come in. One from Alexander. On fusion reactors, do you consider international expansion for delivery?
Yes, yeah, absolutely. So once you've got a prototype, once you've got something that can be replicated, can be commercialized, absolutely, you'll be looking to deliver this across the world, anywhere that it is needed, which is frankly pretty much everywhere. So this is not a technology to be just rolled out here. This is technology to be rolled out across the world.
And another question here from David Dundas. Considering the inherent instability of the torus plasma, what is your opinion of the stellarator?
Of the stellarator?
Mm-hmm. You might need to explain.
So a stellarator, if you've seen a picture of the stellarator, it's well worth a look. What it does is it uses sort of, strangely, I don't actually have a picture of a tokamak to show you, but it sort of looks like with a spherical tokamak, a bit of a chord apple, and your magnetic field is going around the outside. With a stellarator, it sort of uses the geometry as well to contain the plasma. It's a really interesting technology. It has its complexities as well, particularly in manufacture and engineering. I think it's worth pursuing. I think the complexities there do make it difficult, but lots of different fusion technologies. So you've got spherical tokamak, you've got the more donut-shaped one, you've got people looking at different sizes. All of these have different inherent advantages and disadvantages. And again, that's the great thing about all these different approaches. I suspect what will happen is different bits of these different things will work. Yeah,
and then as you said, there's so many different fusion reactor programs at the moment, all backing different horses slightly to a certain extent. Yeah. We did have another question. I just lost it. Just bear with me. Question from Laura. Are organisations still able to register to hear from or join the fusion cluster?
Yes. Yes, absolutely. Our cluster manager, Valerie Jameson, would be really interested. So the people that I put up there are part of the sort of, I think, startup board. I couldn't tell you exactly how to join, but I'd be very happy to send details. Be very happy to join that up for you.
Yeah. I know there's a lady who's been who's a role it is, isn't it? And I can't.
Valerie Jameson. Yes.
That's right. Yeah. So perhaps we can provide Valerie's contact details at some point. Yeah. So, and a question. I think you can answer this very quickly. For fusion, is the same issue to cool down the reactor for nuclear fission, I guess, with impact increasing the temperature or the waterways used, or can it be done differently? So I think you said obviously the reactor or the reaction is very difficult to maintain in the first place. But what's the heating and cooling issues then for a fusion reactor?
Okay. Yeah, it is difficult to maintain the plasma for long periods of time, and that's what a lot of work is going into. The engineering then around how you cool down your components and how you then usefully use that heat is a lot of what is going on in terms of making sure we are as efficient as possible to maximize the power out, and our components last as long as possible. I'm not sure if that answers the question, though. Maybe the person can type if that hasn't answered the question, and I'll type it back.
Sure. Okay, we've heading into the last few minutes, so and I know Shekhar has been answering. I think Mike's been doing a sterling job answering all these questions online, so hopefully you will see a lot of typed responses there. So one from me then, I think, as we close this session out. So as we've heard, Sizewell C will be a replica of Hinkley Point C. SMRs are based on existing nuclear technology, and STEP is based on existing massed fusion machine, if you like. So is there an opportunity for innovation? And if so, in what areas? So Shekhar, I'll come to you first. Where's the innovation in Sizewell C?
I think, Ray, it's a really good question. And I would say the innovation at Sizewell C can probably be described as, on one hand, because Hinkley Point C is a first of a kind project. So we have a good idea as to Hinkley Point C right now in terms of what is it that we need in terms of successfully delivering a UKAEA project. What are the things that could potentially be done slightly differently, and the ways in which, for example, the various supply chain arrangement and other technical aspects need to be considered and driven forward. Already at Hinkley Point C, the lessons derived from constructing Unit 1 of the project, the benefits can be seen in Unit 2, given some of the changes that have been processed and passed through. And the idea is for Sizewell C, in a way, being UKEPR Units 3 and 4, if I can put it that way, to further drive that strand of innovation forward. So all the learnings and lessons that we are deriving from it, hopefully we can further put that into action, and in the kind of arrangements that we are discussing with the supply chain, that is again something, a benefit that we can properly realize. And the other key element of innovation I would describe probably, what I was speaking to during my presentation about these other aspects, such as be it hydrogen, be it direct air capture. These are elements and aspects which really have not been explored in relation to nuclear energy before. These are aspects that I think are increasingly being explored in other parts of the world. Somebody, as in just when we were having this discussion, somebody had emailed me to say that the US Department of Energy recently made a grant in respect of exploring direct air capture with nuclear just a couple of days back. So in that regard, these are really, really innovative technologies where nuclear can play a fairly significant role. And of course, it's not just Sizewell C or big nuclear, as it's nuclear across the piece and spectrum. And the sooner we start looking and exploring these technologies going forward, that is in itself so very important. And of course, government is supporting it. For example, the greenhouse gas removals competition and all the other aspects that are being driven forward. And then hopefully that will continue to be an abiding theme going forward as well.
That's great. Thanks, Shekhar. Mike, where's the innovation then in small modular reactors?
So for us, the innovation, is not in the technology type itself, but it's in the way that we manufacture and build. So that modularization and completely radically overhauling the site build principles. That's where we're putting the innovation. Hopefully to deliver the maximum results.
That's great. Thank you very much. Of course, Heather, I don't think this question applies to you. I think there's, as head of innovation, give me a brief 30-second answer.
Well, there is a huge impetus for innovation in fusion and a low barrier to entry, which I think is a great thing about fusion. It encourages innovation, is encouraging doing things differently, and we're in that stage where it can all still be incorporated in the design. So yeah, it's encouraged, welcomed across every aspect of what we're trying to do.
That's great. Thank you very much. Well, thank you, everyone. Thank you to our three speakers, and thanks to everybody for joining and all your questions. I'm going to close out this session now because we've got a follow-on session. So this webinar has been part of Green Infrastructure Week, and straight after this, the EV Energy Task Force are hosting a session on commercial EV fleet charging requirements. You can join that session and register for all the other events this week at greeninfrastructureweek.com. So thank you very much. Speak again soon. Bye now.